what we have done is that understanding this direct sum and basis and thinking about the dimension and all that, foundation and every in the detail is all about echelon forms. You have to compute an echelon form. As far as I know, there's no way to get around the computational amount that involved in echelon form. This is it. This is just a fundamental amount of computation that you can avoid. This is the minimum amount. So that's one thing. And in all that, although there's in various contexts, is very algebraic. Think that with very algebraic calculation. So if you understand the complex numbers and algebraically, and everything we're doing in here with a scalar in the complex number will work as long as you add and multiply and subtract and divide. So complex number is invented with the square root of -1. Where do you see the square root of -1 for the first time is quadratic formula. Your quadratic formula there's there, and you happen to have a negative number in there. As far as I know, that was really the idea of the invention of this I. That number whose square is a -1, right? So let me challenge you with this idea that there are two numbers in a complex plane that whose square is -1. One is called I. Do you know the other one? There are two numbers whose square is -1. One is called I, and the other one is called -I. Right. So if I decided to write entire mathematics with J, which is not I, but -J, and this one is called -J, right? Then I write the mathematics, instead of I use J, and there's no way to distinguish these two things. Was that originally I or J? There's no way to distinguish these two things in a complex numbers if I write instead of J. This is the sense of isomorphism. If something is isomorphic, you really don't have a way to tell which one is which. Alright? So when you're inventing a number and called it an I, was that really I or -I? Which one are you talking about? Right? Axiom of choice really come into play and it bothers everybody. So in my complex course, I use embedding of the matrix to really show you this is really happening in concrete world. So there's no what is it called? Contradictions, right? So there's a mathematical way to argue that creation of this one is not, the whole mathematics is not going to crumble down because of the contradiction that 1,000 years later somebody discovered. And there's a way to show that this is going to be okay. So that's that. And this, from there, let me compare it with invention of zeros. You all got used to zero, but imagine yourself that you have to explain the concept of a zero to children. There's no problem. Nothingness is all right. But mathematicians like to give birth up to the existence of a nothingness. Isn't that what it is? Zero? Right? There's nothingness is nothing, but mathematicians like to create a thing called that's nothing. That's what zero is, right? With a zero, algebra and all that, we use zero a lot. If you think about it, the fact that we believe the existence of zero become a part of a set, we do algebra on top of it. That was the motivation. If you don't have it, we're going to give a birth to it as long as it doesn't contradict. Then on top of it, we can proceed algebra. And from there, we can still talk about the children's problem using this complex number. That's why mathematicians keep creating this thing that doesn't even exist. That's why they created, but what happened? Quantum mechanics use it. They realize that this is the actually essential nature of what's happening. The complex numbers. Who knew that, right? But before even that, this is invented just to take care of a quadratic equation, right? And then it took care of cubic equation. What does that mean? Solutions of all cubic equation exists inside the quadratic equation solution imaginary number I. And then they went for a fourth equation, quartic equation. They figured it out. all the quadratic equation solution is still written in terms of I. But we only invented this one for quadratic, right? To take care of quadratic. And then they realized that there's no way to figure out dimension 5 or higher. But what does a fundamental theorem? So this is Cartan and those people stopped it there. I can't do this anymore. And then this is called fundamental theorem of algebra, right? Were you able to state it in your test problem? Fundamental theorem of algebra. So if I write down an xn all the way, this is a slightly simpler version, right down to 0, where all this thing is real numbers, right? Isn't that the problem I'm describing? You look at quadratic and cubic and quartic and all that. And if the degree 5, is this going to have a real solution? Can we write the solution in terms of x equals, how does a complex number look like? A plus bi, a is a real number and b is a, this is the shape you see from quadratic formula. Negative b plus minus square root blah 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 b squared minus 4ac divided by 2a. You can group it like this after you're pulling out the magnitude, leaving the negative inside the root. So that's the motivation of real part plus imaginary part in I, because that's how the quadratic formula looks like, right? Whenever you have it. So I was saying cubic and quartic answer can be written like this. Fantastic. But degree 5, they couldn't figure it out. Those ancient people could figure out if it's written like this. But fundamental theorem of algebra says, yes, you can. You can write down the solution of this degree 5, degree 6, degree 2015. The solution of this one will look like this. In fact, all the n solution will look like this. Right? The only question is that computability of this one is the existence. Fundamental theorem of algebra says there exist two real numbers such that it can become 0. But can we actually compute this one? Computability. No. The answer is no. There's no notation we have that we can write it down. But approximately down to 1,000 digits, you can do that. But there's no precise notation to describe what this A and B are. So computability goes, but we have existence of real number to take care of that. So that was the better version of a fundamental theorem of algebra that students feel it. That's what it's talking about. But the book says even if it is a complex coefficient, this one still has solutions, right? Stronger version. But this statement follows from there. That's fundamental theorem of algebra. The proof of this one has a long history. Gauss failed. The famous Euler failed to completely prove it, right? Legendre failed. You name it. Bernoulli couldn't do it. It was actually late 1800s. It was surprisingly late. They completely proved. But they all knew. It seems like that's it. This invention of imaginary quadratic took care of entire polynomial world. And in our complex numbers, last semester we even solved this type of problems. Not only polynomial, sine x equals -2 has a solution in complex numbers. Sine only reaches 1 and -1, right? But this guy, so complex number was a lot more surprising world than human being initially thought. And these days, quantum mechanical world is as natural than how this one fit into. Any general question about complex numbers? All right, let me explain a bit more about complex numbers. So there is this two complex numbers, right? Humble beginning of a plus bi and w is equals c plus di, right? And do you know how to add and subtract and multiply? I think we did something like this in chapter 1. There was a little bit of exercise, right? So that's like a vector, so you can treat it like a vector. So here's a geometric version. So this is a comma b in the xy plane, right? But it seems like if you understand how you add and subtract these two complex numbers, there's no mingling between real part and imaginary part. You know the real part and imaginary part? This real part is the coefficient. An imaginary part of z It's just that coefficient, right? When you add and subtract, there was a mix of real part and there's just imaginary part interacting together. So if you look at it here, they look a lot like a two-dimensional vectors. Don't you think? A comma B and C comma D. When they add it, really like a vector addition. So this is kind of representing A plus BI. It's really true. But you don't multiply vector to vector, right? But here you can multiply Z to W. So it's more structured. So you know how to multiply these things, remember? Yeah. So we have even division. That was tricky. So if I have A plus BI, how do you turn this one into real number plus another real number times I? How do you do that? We multiply something to the denominator and numerator to turn this one into real numbers, and you can split it. What was that? C minus di and A plus, not A plus bi, C minus di. Do you remember what they called? The C minus di is what of C plus di? Complex conjugate, right? If you multiply that, it becomes a real number. So you can see that becomes, so it has this richer structure, but you can look at complex number as complex number is a dimension challenging over real numbers. I've never used this in notation, but here, if you want to look at complex number of a vector space with a scalar as a real number, what is the dimension of this one? Sorry about this. I think this one is representing. This is, if I sketch it like this, without this one, everybody will say that's a two-dimensional vector space, right? Isn't that what this one is, exactly? Not about addition and multiplication. This as a vector space, we don't multiply two vectors, right? We just add and subtract and scalar multiple coming from real numbers. So what is the dimension of the complex number as a vector spaces with a scalar in the real coefficients? 2. Okay? That's the dimension 2 there. All right? So we say there is an isomorphism to R2. T, right? Where is this A plus BI going? Do you know? Column vector? What kind of column vector is that going to be? A and B. And you show this is surjective and injective, things like that, and then we know these are isomorphic to each other, right? When they're isomorphic, the dimension is the same. This is a dimension 2, and that's going to be dimension 2. Understanding this is a vector space over same scalar field. All right? That's usually the mathematician's preferred way of dealing with the dimensions. All right, so C, T is isomorphism. Therefore, dimension of C is equal to the dimension of R2. And here you're specifying, clarifying that we're looking at the C as a vector space over R coefficient. Make sense? Therefore, it's 2. That's the vector. But if you look at it as a, this is a confusing statement, dimension of a complex numbers over a complex numbers. This is supposed to be a field. You can add and subtract and multiply and divide. And here I was trying to explain, you can do that with the C, right? And this one is just 1. Right, the whole thing is this 1 times C. Just like everything is 1 is a basis member to reach all the other member in the C. You just multiply that number. It's just as the same thing. If you understand this one, that's going to be a simple statement. R to the first. R to the first is a column vector of 1 entry, right? What is the dimension of this one? Dimension 1. There's only one vector, which is called 1, 0, I mean just a 1. You multiply all the scalar to that, you will reach all the other R. And here's the same. The generator is 1. The length 1 column vector. If you multiply all the C, then you can reach all the other C's by scalar. Scalar itself is a one-dimensional vector space. All right? So let's challenge ourselves a little bit more. How about C2? Do you see C2? Nobody sees C2. Nobody sees C2. C itself is dimension 2, right? How about C2? It's like dimension 4. You can't picture this, right? But it looks like this. Simple. Here's Z and W. Where Z and W is coming from where? Complex numbers. Right? Complex numbers. So this one has a dimension. What? Over complex numbers. 2. That's right. Dimension 2. All right. You can still look at it as a real complex, real vector field. If I multiply real number, it remains inside C, so it's okay. So you can write down, all right, I can do this, and your answer is 2 times the dimension of C and C2. Because each of the dimensions split into 2 more, real part and imaginary part. Well, if I just keep saying things like that, maybe it's true, but how you're going to show things like this is an isomorphism. You're constructing isomorphism, all right? How would you construct the isomorphism from to see this one in here? All right, I have C2 as a vector space over real number here, right? And then you construct what kind of column vector space? What is the number? I'm about to construct a vector space with a scalar r from C2 to r to the what? If you believe this is true, 4, isn't it? 4, 2 times 2, 4. All right, so if I have two things, Z and W, that's a two-dimensional complex vector, and then where's it going to go? Under that map. Or we're going to split this Z into 2 parts, right? There's a 2-letter thing is called, we're going to just take the real part of that, and we're going to take the imaginary part of that, right? And stick that real part of the second vector and imaginary part of the second vector. All right? So this should be a linear, and just injective, and surjective, and then you show, hey, that's isomorphism. Then dimension of this one is dimension of that one, right? Therefore, dimension 4. Make sense? That's what they're creating right now. This, because of the geometric, is so familiar. Or you see this number line since you're young. So it's geometrically, now when you pass to scalar to C, everybody's puzzled, but you have to just stick to algebraically, there's no problem. Just multiplying Z to vector V. That's what they're creating. Multiplying complex number Z to vector, as long as this makes sense, that's going to be vector space over the scalar field C. Okay? Yeah. All right. So here's more things that I need to write down. More about the basics of a complex number, not as a scalar field of a vector space, is that the Z-bar notation. You know the Z-bar notation? It's A minus BI. That was used when you changed denominator to real. And what are the things there? Important thing about the Z-bar is if you add first and conjugate later. This is the order of operation. Don't think this is trivial. There's no way to trivially explain this. You actually have to write it down one at a time. It's notationally, is equal to you conjugate first, add later. Order of different. Remember one of the homework problem, the bar, right? S bar, T bar, that was homework problem. That's exactly the same nature. You have to check it. This is true though. More interesting, if you multiply first, and then this is even more non-trivial. Multiply first and conjugate later is a conjugate first and multiply later. This is true. Now, equal to each other. And there's also the z bar, not z bar, absolute value of z. Remember this absolute value of z? Length of a vector, if you interpret the z as a vector, right? So this one was square root of a squared plus b squared. Alright? So here's vector a comma b. The length of this vector, you probably did that in Calc 3, length of a vector and things like that. That is also applicable to the complex number when you identify that in xy plane. Right? And also there's a neat connection. There's a, alright, if I square this length, then what disappears is square root, right? And then if you multiply z to the z bar, you exactly get a squared plus b squared. A plus bi times a minus bi becomes a squared plus b squared. So these are the basic rules for complex first hour complex algebra, and there are actually of course more, and that's the important thing. All right. Then we're reviewing this to understand the following: the fundamental theorem of algebra. What was the statement they gave about the fundamental theorem of algebra? All complex coefficient polynomial. Isn't that right? All right. All polynomials with a complex coefficient have what? A complex root. Right? A complex root. They don't say complex, but let me emphasize a complex root. Okay? That's the fundamental theorem of algebra. So, but you will see this in the real context, just like I said that there. If it is a real polynomial, p is coming from polynomial with real coefficients. That's notation, right? And this one will be p of c, polynomial with complex coefficients. Then, the corollary, p factors into linear alpha 1 to alpha m. There's a linear factor times quadratic factors, x squared plus beta 1 x gamma 1 dot all the way to x squared plus beta l to gamma l x. There's a bunch of linear factor, there's a bunch of quadratic factor, where all this thing satisfy this condition, b beta k squared minus 4 times gamma k is less than 0. Do you know what that means? Beta squared minus 4 times gamma. Quadratic formula, right? Inside is a 0, so they don't have real roots. You can't factor into real part because this indicates that there's no real roots. This is irreducible, the smallest degree that you can reduce it with a real coefficient. So this one implies the following, like that. Actually, if you were just concerned about polynomial with real coefficient, what happens is that it's like this. And can we compute this alpha 1 and alpha m in practice? No. It's just the existence of these real numbers. Okay? The proof goes like this. It's rather simple and it's neat. Goes like this. If lambda is a complex 0, complex root, then lambda bar is also a complex root. This is a crucial statement, right? So let's say p is given by this polynomial, k going from 0 to n is not used here, so I'm going to use n of a k and x to the k. This is a polynomial where all the ak is inside the real number. That's the real coefficient polynomial, right? And we have a p of lambda that is a 0. So we have ak and lambda to the k and going from 0 to n. That is going to be 0, right? And we want to show lambda bar also satisfy. This one is a complex conjugate. So what they do is that you hit this entire left-hand side, which is 0, complex conjugate. What is a complex conjugate of 0? Is 0. And you hit complex conjugate in here, the whole thing, lambda k like that. That complex splits over addition, right? No matter how many, so they split it. It goes inside a k bar times lambda k power bar like this. Do you see that? Because of this z bar plus w bar. If you have 3 of them, they're all bar in individual terms, right? And they also split over like this. Because over multiplication, they split it, right? What do you know about AK bar? Clues here. If there's a real number, it's going to look like this. 0 times I, right? Complex conjugate will just change the sign of that, but that's 0. So real number is untouched by complex conjugation. So that's exactly AK. Untouched. The coefficient survives. And because it's a multiplication of k things, you can go inside like that. Because lambda, 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 whole bar is a lambda bar, lambda bar, lambda bar, and so on. So isn't that also 0? And isn't that exactly the same polynomial with a different thing sticked in? The lambda bar is also a complex root. Make sense? Yeah. So if it is really complex numbers, then fundamental theorem of calculus says that it splits to everything. It's like lambda 1, lambda 2. Everywhere it's going to have complex roots. That's fundamental theorem. If that one has one complex root, you factor it out. Next one, again, you use the fundamental theorem to the lower degree. Again, keep factoring out. You're going to have this one in here. If this is a really complex number, there's no the imaginary part there. Lambda bar must be somewhere here, right? Because we know lambda bar must appear. So they paired up like this. X minus lambda 1, x minus lambda 1 bar must be somewhere up there, which is like lambda k. And if you pair them up like this, and if you multiply this one out, x squared minus lambda 1 bar, x times lambda 1 and lambda 1 bar. So if you approach just with a plus bi, a minus bi, and to that, this become a real number because they cancel. And if you multiply, it becomes a squared plus b squared, also real numbers. Therefore, as you paired up the linear factors with a complex conjugate, that polynomial becomes real polynomial as you pair them up. And their zeros are complex, therefore you must satisfy this condition. And that shows that all the real coefficient polynomial must factor like this, although computing those coefficients is impractical. Precisely. Computing is impractical. So we're going on too long.